Hello everyone, my name is Thandolwethu, a master's student at the University of Pretoria, South Africa. Today I will be discussing my MSc study, which aims on assessing variation in hard and soft tissue European facial morphology matrices for 3D facial approximation. An intercorrelated relationship in both form and function between skeletal structures and overlying soft tissues of the face is expected to exist based on biological reasons. This intercorrelation has been of scientific interest in many disciplines, such as craniofacial surgery, orthodontics, and forensics and anthropology, specifically facial approximation, for developing more accurate facial recognition methods. Facial approximation methods are based on the assumed morphological relationship between the bony structures and soft tissue features of the face. A facial estimate can be generated by correlating selected cranial landmarks of the unknown skull to soft tissue structures. Facial approximation has moved towards more automated 3D and computerized methods to increase the accuracy of facial approximation. Craniofacial reconstruction, or CFR, also known as facial approximation, is a technique applied in forensics based on both scientific methods and artistic skill. CFR methods are based on the assumed relationship between the soft tissue envelope of the cranium and the underlying skull substrate. As recommended by the Scientific Working Group for Forensic Anthropology, the aim of craniofacial reconstruction is to approximate the antemortem facial appearance, estimate identification, and captivate the public. By establishing a relationship between selected cranial landmarks and facial soft tissue structures, a facial estimate can be generated from a database of ancestry, age, and sex-specific individuals matching the unknown individual's biological profile. Traditional CFR methods are categorized into 2D or 3D manual reconstruction based on utilizing modeling clay or plasticine to build up tissue depth on the dry skull. Recently, computer science and 3D imaging technologies have advanced and improved, leading to the development of new rapid and efficient computer-aided CFR methods. Cone-Beam Computed Tomography, or CBCT, is a radiographic imaging procedure that generates a 3D image using an X-ray source and detector fixed to a rotating gantry. The entire chosen field of view is incorporated to produce a 3D volumetric image. CBCT systems rotate around the patient, capturing data using a cone-shaped X-ray beam to reconstruct a 3D image of the teeth, mouth, jaw, neck, ears, nose, and throat. Facial approximation studies have been tested on several populations. However, no research has been published on European populations using CBCT scans for 3D computer-assisted CFR methods. The aim of our study is to evaluate the influence of known factors of ancestry, sex, age, and covariates on the facial morphology matrices of European population groups using Geometric Morphometrics, or GMM, on CBCT scans. The objectives are to extract anatomical shape data using anatomical landmarks and sliding landmarks on hard and soft tissue 3D reconstructions segmented from CBCT scans, to assess the covariation between hard and soft tissue facial shape matrices using geometric morphometric methods and its dependence on known factors of ancestry, sex, and age. And lastly, to compare Irish facial morphology matrices to French, European, and white South African statistical data. For our materials and methods, CBCT scans will be collected from St. James University Hospital in Dublin, Cork University Hospital, and South Infirmary, Victoria University Hospital in Cork, in association with the University College Cork. The MSc candidates will benefit from a 2-month research mobility to the University College Dublin under the co-supervision of Dr. Robin Finney, fully covered by the Durasana Plus project for data collection. Just to briefly explain the Durasana Plus project, this project is a building project co-founded by the Erasmus Plus program of the European Union in higher education aimed at improving health sciences education in Southern Africa. The Durasana Plus project consists of 5 partner institutions in Southern Africa, namely the University of Pretoria, the Sefako Magatho Health Sciences University, the University of Witwatersrand, the University of Namibia, and the Walwitshire Health Training Center. The Plus project is led by the University of Pretoria as the coordinating institution. Furthermore, 3 European program institutions, namely the University College Dublin in Ireland, the University of Turku in Finland, and the Maastricht University in the Netherlands, complete the Plus consortium. Now back to our materials and methods. All patient data will be anonymized, with only the biological profile information pertinent to the current study recorded for analysis, which are sex, age, and ancestry. For consistency during data collection, patients will be excluded from the sample if they present with conditions that could affect the morphology of the face and subsequent analysis results. Such conditions include any pathologies, trauma, surgical intervention, or deformities. Then lastly, for our comparative shape data, this data will derive from 108 French and 76 white South African population groups from a previous research project. To collect information on the shape of hard and soft tissue facial matrices, the study will be approached as an automated landmark-based geometric morphometric study to extract and compare information encoded in 3D surface reconstructions. The free software MeVisLab 2.7.1 will be used for data collection. The CBCT images will be loaded into MeVisLab for data processing, which includes segmentation and the reconstruction of 3D meshes, and for anatomical shape data extraction using a non-rigid generic mesh-to-mesh matching algorithm known as the automatic landmarking method. All statistical analyses for the study will be conducted on the R Studio software using R Morpho packages, Geomorph, and FF-Manova. The shape data will be analyzed through GMM methods to evaluate the influence of ancestry, sex, age, and covariates on the hard and soft tissue facial morphology matrices of the European population. As previously mentioned, the study will be approached as an automated landmark-based geometric morphometric study. The primary basis of this approach is to digitize X, Y, Z coordinate positions of landmarks, which are points representing the spatial positions of homologous structures in 2 or 3 dimensions. Variation will be studied by assessing shape matrices from landmarks on hard and soft tissue structures. The utilization of biological landmarks ensures that each identified point is in the same location on all other surfaces in the sample. To ensure homology and comparability between studies, classic definitions of craniometric and capillometric landmarks will be used. Regions of interest in the study will include hard and soft tissue midfacial matrices, facial lateral hard and soft tissue matrices, and hard and soft auditory matrices. These landmarks allow for comprehensive and multivariate analysis of biological shape variation among structures. The landmarks will be positioned on the 3D hard and soft tissue surfaces using the automatic landmarking method. The method generates a reference template that can be projected onto every reconstructed surface, resulting in a dense point-based anatomical correspondence between all subjects. Before registration, all surfaces will be repositioned into the same coordinate system using a surface mesh initialization procedure. A reference template will be created using a non-rigid surface registration process. Lastly, the reference templates will be indicated once by place landmarks. Each landmark placed on the reference template will be projected onto the surface of every subject, resulting in a dense point-based anatomical correspondence between all subjects. This method allows the exploitation of all geometric information encoded within these landmarks, thus recording all landmark coordinates within a common coordinate system for further statistical analysis. The hard tissue regions of interest will be indicated on the facial skeleton. The midfacial matrix will consist of 43 standard craniometric landmarks, which will be further divided into the left and right orbits, left and right nasal bones, anterior nasal aperture, left and right zygoma, and left and right maxillae. For the midfacial matrix, the left and right orbits, left and right nasal bones, and anterior nasal aperture will consist of 7, 11, and 10 landmarks respectively. The facial lateral matrix will consist of 10 landmarks on either side on the zygoma and 3 landmarks on the maxilla. The soft tissue regions of interest will be indicated on the soft tissue surfaces. A total of 50 capillometric landmarks will be automatically placed on the sample. The soft tissue auditory matrix will consist of 19 standard fixed landmarks on either ear. Landmarks will also be indicated on the other soft tissue features of the face, which are the eyes, mouth, and nose. The eyes will consist of 4 landmarks in 2 bilateral pairs, and 8 landmarks will be indicated on the mouth, which are 2 median landmarks and 3 bilateral pairs. 5 median landmarks and 7 bilateral pairs will be indicated on the external nose. Each matrix will be indicated separately on the surfaces for every individual to ensure a maximum sample size. For shape variation analysis, quantification and visualization of covariance between the hard and soft tissue facial matrices and the covariates will be performed on the complete sample using GMM methods. To assess shape variation between the populations, mainly 3 tests will be conducted. Firstly, a MANOVA, which is a parametric test, and then a 50-50 MANOVA and permutation testing, which are both non-parametric tests. The respective MANOVA tests will determine whether or not the independent growing variables, which are ancestry, sex, and age, simultaneously explain a statistically significant amount of variance in the dependent variable, which is shape variation. For the permutation testing, a chosen factor such as ancestry, age, or sex will be calculated and compared to values from the sample where ancestry, age, or sex are repeatedly randomly assigned. Then lastly, standard discriminant function analysis will also be applied for sex and ancestry classification purposes by finding linear combinations of variables that display intergroup differences, which in turn will define linear discriminant functions. Correlations between the hard tissue structures underlying the face and soft facial tissues will be calculated with 2 blocks partial least squares analyses. This analysis assesses the degree of association between 2 blocks of precocities aligned coordinates, which are pose invariant shape coordinates obtained through a generalized precocity superimposition, or GPS, of the raw coordinates from the manually and automatically placed landmarks. A GPS reduces the sum of the squared distances between corresponding anatomical points by aligning the configurations of landmarks and removing differences due to translation and rotation among all individuals. The remaining shape information forms a set of precocities coordinates. The correlations that will be assessed between the soft tissue auditory matrix and the soft tissue midfacial matrix, the soft tissue auditory matrix and the hard tissue midfacial matrix, the soft tissue auditory matrix and the facial lateral matrix, the facial lateral matrix and the hard tissue midfacial matrix, and then lastly, the facial lateral matrix and the soft tissue midfacial matrix. Human facial morphology differs between individuals. Historically, craniofacial genetic research has mainly focused on identifying the causes of craniofacial variation, and only recently has there been a need to identify the biological origin of normal range facial variation. This initiative has been facilitated by the availability of low-cost, high-resolution 3D systems which are able to capture the facial details of large numbers of individuals quickly and accurately. Assessing facial morphology matrices using CBCT scans allows us to investigate the extent of facial variation within and between various populations, therefore providing a better understanding of European craniofacial shape variation. In conclusion, the implications of the study may provide a better understanding of facial shape variation and the factors that shape facial morphology between and within various populations. Preliminary results suggest the likely need for population-specific databases for estimating the shape of facial matrices in South African, Irish, and French populations for 3D computer-assisted CFR methods. The application of 3-dimensional scan models offers a valuable resource for studying craniofacial variation and forms an essential part in creating facial recognition software tuned for different populations based on relationships between hard and soft tissue facial morphology and additional covariates. And that brings us to an end. Thank you for watching.